The Sun. The Sun is a 4.5 billion-year-old yellow dwarf star, a hot glowing ball of hydrogen and helium, at the center of our solar system. Its gravity holds everything from the biggest planets to tiny debris in its orbit. It is a dynamic star, constantly changing and sending energy out into space. The Sun is the largest object in our solar system. Its diameter is about 865,000 miles, 1.4 million kilometers. It is a medium-sized self-luminous gaseous mass that contains 99.9% of all the matter in the solar system. It is of average brightness for a star. The Sun has been called by many names. The Latin word for sun is sol, which is the main adjective for all things sun-related, solar. Helios, the sun god in ancient Greek mythology, lends his name to many sun-related terms as well, such as aliosphere and alioseismology. The science of studying the sun and its influence throughout the solar system is called aliophysics. Astronomical symbol, the modern astronomical symbol for the sun, a circled dot, was first used in the Renaissance. Roman name, Sol, Greek name, Helios, role in mythology, the god of the sun. Full disk photo taken by NASA's SDO on November 17, 2010. Most atoms in the sun exist as plasma, a fourth state of matter made up of superheated gas with a positive electrical charge. Structure. The sun is composed of gas. It has no solid surface. However, it still has a defined structure. The three major structural areas or regions of the sun are 1. Core, the center of the sun, comprising 25% of its radius. 2. Radiative zone, the section immediately surrounding the core, comprising 45% of its radius. 3. Convective zone, the outermost ring of the sun, comprising the 30% its radius. Above the surface of the sun is its atmosphere, which consists of 3 parts. 4. The photosphere, the innermost part of the sun's atmosphere and the only part we can see. 5. Chromosphere, the area between the photosphere and the corona, hotter than the photosphere. 6. Corona, the extremely hot outermost layer, extending outward several million miles from the chromosphere. Some features of the sun. 7. Sunspots, dark, cool areas appearing on the photosphere. 8. Granules, are places within the photosphere where hot bright material reaches the surface. 9. Prominences, are arches or clouds of gases rising from the chromosphere and orienting themselves along the magnetic lines from sunspot pairs. Regions, 1. Core, 2. Radiative zone, 3. Convective zone. Atmospheres, 4. Photosphere, 5. Chromosphere, 6. Corona. Features, 7. Sunspot, 8. Granules, 9. Prominences, others like solar flares, spicules, etc. The sun layers drawn to scale. Core. Radiative zone. Convective zone. Photosphere. Chromosphere. Corona. Sunspot. Granule. Prominence. Flare. The sun has several regions. The interior regions include the core, the radiative zone, and the convection zone. Moving outward, the visible surface or photosphere is next, then the chromosphere, followed by the transition zone, and then the corona, the sun's expansive outer atmosphere. Not all scientists refer to the transition zone as its own region, it is simply the thin layer where the chromosphere rapidly heats and becomes the corona. The part of the sun commonly called its surface is the photosphere. The word photosphere means light sphere, which is apt because this is the layer that emits the most visible light. It's what we see from Earth with our eyes. But never look directly at the sun without protecting your eyes. Thickness of each layer of the sun. Solar core, 86,000 miles. Radiative zone, 233,000 miles. Convection zone, 113,000 miles. Photosphere, 250 miles. Chromosphere, 1,050 miles. Transition zone, 60 miles. Corona, 3.1 million miles, approximate. The photosphere, chromosphere, and corona are all part of the sun's atmosphere. The corona is sometimes casually referred to as the sun's atmosphere, but it is actually the sun's upper atmosphere. The sun's atmosphere is where we see features such as sunspots, coronal holes, and solar flares. Solar feature, sunspots. They look like dark holes in the sun, but they are actually areas that are slightly cooler than the surrounding photosphere. Sunspots are created where bits of the sun's magnetic field poke out from the interior into the sun's atmosphere. Lasting from days to months, sunspots range in size from 1,000 to 100,000 miles, 1,600 to 160,900 kilometers. Sun feature, solar prominence. A solar prominence, also known as a filament when viewed against the solar disk, is a large, bright feature extending outward from the sun's surface. Prominences are anchored to the sun's surface in the photosphere, and extend outwards into the sun's hot outer atmosphere, called the corona. A prominence is a snake-like structure made of cooler, denser solar material that is suspended above the sun's surface by a strong local magnetic field. When they are viewed against the solar disk, head-on rather than off the visible edge, they are called filaments. Prominences can erupt and the magnetic structure becomes unstable, flinging their plasma outward in a blast called a coronal mass ejection. Sun feature, solar flare. This image, captured by NASA's Solar Dynamics Observatory on June 20, 2013, shows the bright light of a solar flare on the left side of the sun. Sun feature, spicules. At any given moment, as many as 10 million wild jets of solar material burst up from the sun's surface. Known as spicules, these grass-like tendrils of plasma erupt as fast as 60 miles per second, 100 kilometers per second, and can reach lengths of 6,000 miles, 9,700 kilometers, before collapsing. Sun feature, coronal holes. A coronal hole is a patch of the sun's atmosphere with much lower density than the surrounding areas. In ultraviolet views of the sun, coronal holes appear as dark splotches. These regions are where the sun's magnetic field lines are connected directly to interplanetary space, allowing solar material to escape out in a high-speed stream of solar wind, leaving a dark hole near the surface of the sun. Sun and planet size comparison. Ordered in descending size, left to right, top to bottom. The Sun. Jupiter and Saturn. Uranus and Neptune. Earth, Venus, Mars and Mercury. The size of our Sun compared to other stars. Our Sun is impressive, but how does it compare to other stars? There are billions more stars in the Milky Way galaxy. And there are many, many more in the rest of the universe. Our Sun is an average-sized star. There are bigger stars, and there are smaller stars. There are stars that are 100 times bigger in diameter than our Sun. There are also stars that are just 1/10 the size of our Sun. The Sun's energy. The Sun produces an amazing amount of light and heat through nuclear reactions. The process that produces the Sun's energy is called nuclear fusion. In nuclear fusion, Two atoms come together to produce a heavier atom. Fusion reactions release energy and tiny elementary particles. Fusion is the process in which light elements are squeezed under immense pressure and temperature into new heavier elements. Every second, the Sun fuses about 600 million metric tons of hydrogen. That's the mass of 102 Great Pyramids of Giza, 1,812 Empire State Buildings, or nearly all of the fish on Earth by some estimates. Earth would not have any life on it without the Sun's energy, which reaches Earth in the form of heat and light. This energy warms our days and illuminates our world. Green plants absorb sunlight and convert it to food, which these plants then use to live and grow. In this process, the plants give off the oxygen that animals breathe. Animals eat these plants for nourishment. All plant and animal life relies on the Sun's presence. Role in the solar system. The Sun's gravitational pull holds the solar system together. The planets, asteroids, comets, and dust that make up our solar system are strongly attracted to the Sun's huge mass. This gravitational attraction keeps these bodies in orbit around the Sun. Magnetosphere. The Sun generates magnetic fields that extend out into space to form the interplanetary magnetic field, the magnetic field that pervades our solar system. The field is carried through the solar system by the solar wind, a stream of electrically charged gas blowing outward from the Sun in all directions. The vast bubble of space dominated by the Sun's magnetic field is called the heliosphere. Since the Sun rotates, the magnetic field spins out into a large rotating spiral, known as the Parker spiral. This spiral has a shape something like the pattern of water from a rotating garden sprinkler. The death of a sun-like star. Sun-like star. Longest, most stable period of a star's life converts hydrogen to helium, radiating heat and light. Red giant. Nuclear fuel depletes, core contracts, shell expands. Nebula. Outer layers drift off into space in sphere-like pattern. White dwarf. Star cools and shrinks, becoming only a few thousand miles across, no nuclear reaction. Black dwarf. Star loses all heat to space and becomes cold and dark carbon ball. Life cycle of the Sun. The Sun was formed about 4.57 billion years ago when a hydrogen molecular cloud collapsed. The Sun will spend a total of approximately 10 billion years as a main sequence star. It will enter a red giant phase, its outer layers expanding as the hydrogen fuel in the core is consumed and the core contracts and heats up. Following the red giant phase, intense thermal pulsations will cause the Sun to throw off its outer layers, forming a planetary nebula. The only object that will remain after the outer layers are ejected is the extremely hot stellar core, which will slowly cool and fade as a white dwarf over many billions of years. The fate of the Sun. Like all stars, our Sun will eventually run out of energy. When it starts to die, the Sun will expand into a red giant star, becoming so large that it will engulf Mercury, Venus, and possibly Earth. Scientists predict the Sun is a little less than halfway through its lifetime and will last another 5 billion years or more before it becomes a white dwarf. In the meantime, the Sun will continue to play a critical role in the system that bears its name. The Sun's protective magnetic field, tremendous gravitational pull, and ability to create vast amount of energy will protect, contain, and give life to our solar system.